Okay, great. Thank you. Thank you all for coming, and thank the organizers for inviting me and for organizing this series of talks. I think it's very useful to listen to all the different kind of thermal research people have been doing. It's been very enjoyable to listen to the other talks, and let's see if I can try to provide something useful for you guys. So this talk is based in a recent paper I write together with collaborators in Jena, Martin Ammon, Jette Germeros, and Christoph Silling. This is the archive number. Jette and Christoph are two very promising students in our group, so keep an eye out for them in the future. Okay, so a bit of motivation, although in this crowd, I don't think I need to motivate too much the goals. So the main motivation behind this work is the fact that holography is an excellent tool to study dynamics at finite temperature, and also the physics at finite temperature allows a window into understanding the physics of black holes, thanks to holography. However, a lot of the study of finite temperature holography is done in a Euclidean signature. But as everyone knows, if I want to study the physics of out of equilibrium systems, I really need to consider Lorentzian evolution, real-time physics. And in that case, there is several complications that emerge in comparison with the Euclidean setting. There is the question of time ordering, and then one need to make sure to be able to define correlators in systems that are strongly coupled, in which the usual assumptions for the Feynman path integral don't always hold. Fortunately, all of these can be captured in the formalism of the Schwinger-Keldysh contours. And the Schwinger-Keldysh, the holographic dual for the traditional Schwinger-Keldysh contour has been known for a while in parallel works by Glorioso, Crossley, and Liu, and similarly works by Jana, Loganayagam, and Rangamani. But there is a elephant in the room, which is that Schwinger-Keldysh contours, despite the fact that they are very useful tools to study real-time physics, they do not capture all the possible correlators we may want to study in physics out of equilibrium. Famously, there is the out-of-time order 4-point function, which is closely related to the physics of quantum chaos, which is outside the remit of what a traditional Schwinger-Keldysh contour can capture. So we need to generalize the usual contours prescriptions of Schwinger-Keldysh, and correspondingly, we also need to find a new holographic dual to these more complicated time contours. So that's more or less the problem we would like to attack. By the way, I forgot to say it, but feel free to interrupt me at any time. The only problem is that you need to really speak out because I am not seeing everyone present. So if you just like raise your hand or something, I will not see it probably. So at any moment, just shout and stop me, and I'll be happy to attempt to answer any questions. Okay, so let's do again, in this crowd, this may not be very necessary, but let's do a quick review of the Schwinger-Keldysh formalism so that we are all in the same footing in terms of notation. So here I am depicting the complexified time contour that allows me to compute correlators by introducing sources along the forward or backward branch in this complexified time contour. And in general, I can capture any kind of correlator that is capturable with these contours in terms of this generating functional. So this is just a generalization of the conventional Feynman generating functional, which is usually time order. This generalizes the generating functional by considering a path integral not along the conventional time ordering from minus infinity to infinity, but along this contour that starts at some initial time, goes as late as one needs, and then it goes back in time. Here I am assuming, and I will assume throughout the talk, that I want to compute thermal correlators, in which case I have a segment of Euclidean evolution whose job is just to prepare the state in thermal equilibrium. So if I want to compute any kind of time order, anti-time order, or retarded correlator, things like that, I can do it if I am able to evaluate the generating functional by the usual functional derivative method. So any correlator of this form one can capture using the Schwinger-Keldysh contour. This is a very large family. Of course, it includes time ordering, anti-time ordering, but also other interesting causal ordering, such as retarded correlators, Keldysh correlators, advanced correlators, etc. So it's a very large family. But as I mentioned a minute ago, there are still correlators that are not of this form that I would like to be able to analyze. And to do that, I need to consider these kinds of objects in which instead of just two time evolutions, one forward and one backwards, I need to have more time evolutions in order to have the corresponding operator insertions to capture any correlator I want. Here I am depicting the kind of insertion one would need for the out-of-time order correlator. But more generally, one would like to compute the generating functional for all correlators. So if I have enough back and forward time contours, I will be able to compute any kind of time ordering I wish, ideally. But now, something that it was mentioned in a talk before is that when one does these Schwinger-Keldysh contours, there are constraints that are imposed on the generating functional. Two of them that are important is the oh, what are we, there, is the constraints of microscopic unitarity and the KMS condition. So I am assuming that the underlying theory I want to study undergoes unitary time evolution. Similarly, since I am considered correlators in the thermal state, the defining property of thermal correlators is that they obey the KMS condition. And that imposes constraints in the kind of objects that will appear when I compute this generating functional. Here is just a pictorial example of how unitarity works. If I have one of these operators inserted in the forward moving branch, usually referred as right, I can trade it for a left operator as long as there is no other operator in between, right? I can just slide it forward in the contour without any problem. But that means that if I have a collection of right correlators, I can trade them off for left correlators without any penalty. To capture this a bit more concretely, it's useful to introduce a new basis instead of the usual right-left basis for operators. I will consider this average difference basis. And then the property of unitarity simply tells me that if I have correlators that are all different, I can always just slide them across the contour and they will annihilate each other and that will just give zero. Similarly, the property of a thermal correlator, which is KMS, is that I can permute operators paying the price that I need to do an evolution across the Euclidean circle. This just follows from the cyclicity of the trace and the invertibility of the thermal density matrix. So in the same way, one introduces the average different basis to capture unitarity, one can introduce another basis, which here I call difference KMS, but in the literature is often just called the advanced retarded basis, in which I have the all difference operators, which still will implement unitarity, but I then introduce these KMS operators, in which I consider the difference between a right operator and its KMS translated partner. And then the condition of KMS just translates in a similar condition as the unitarity condition, that if I have just KMS operators, now not only can I slide them and cancel them against each other along the real part of the contour, I can just take one of them and go around the Euclidean circle and move them into a different contour without any penalty. Again, as long as I don't have some other operator obstructing this operation. I should mention that these are somehow the weakest conditions one can impose. I wrote them in momentum space, and because I like to use momentum space, and we will use momentum space through a talk. But in position space, one can impose stronger conditions. For example, for the unitarity condition, I don't really need all the operators to be difference operators. I only need the latest operator, the one that is forward in the contour, to be a difference operator, right? So, and similarly for the KMS condition, but those are a bit more complicated to implement in the Fourier domain, so I will not really use them uh, throughout the construction. The important thing is that these two conditions will be the guiding principles I will use to construct the holographic dual. So whatever this holographic dual will be, I will always try to see if it satisfies the unitarity and KMS conditions, or the corresponding generalization when I have not the Schwinger-Keldysh contour, but these multi-fold contours. So in the case of having these generalized Schwinger-Keldysh contours, I can introduce a complicated basis. This just generalizes the different KMS bases from earlier. I have one that is the KMS operator, and then I have all the different operators. I will have many of them because you can imagine I have all these back and forth contours, and I can always just slide operators either to the furthermost point of the contour and annihilate them, or on the other on the backward contours and annihilate them there. Right? So I have now more of these different operators. I only have one KMS operator because thermal correlators, I only have one thermal circle I can go around, so I can only go from the last branch to the first branch along the thermal circle. Let me know if this is, to me, this has become a bit second nature to imagine these contours, but stop me at any moment if what I say doesn't make any sense. So in order to construct the generating functional, I also need the corresponding basis for the sources. This is just a natural extension. The only difference is that usually in the literature, for the Schwinger-Keldysh contour, this is the generalized case, but for the twofold contour, the bases are usually chosen for some reason to be off diagonal. So the average basis sources the difference operator and vice versa. As you generalize to more contours, that becomes very hard to keep track. So here I introduce the basis so that the KMS sources a KMS operator, and similarly for all the difference operators. So that's a bit of the field theory introduction. This is the kind of objects we want to construct. If you like quantum field theory, then you can just go and try to compute the kinds of generating functionals in I don't know, 5 to the 4, whatever theory is manageable. But what I want to do is not to do that, but instead try to construct holographic duals that allow me to study the generating functionals. Right? So as I said, the case of the normal Schwinger-Keldysh contour is known and is what is known as the gravitational Schwinger-Keldysh contour, GRSK. And here I introduce a 2 to distinguish it because I'm going to generalize this to many time folds, right? So let's review quickly how these gravitational Schwinger-Keldysh geometries work. Here, once again, I have my Schwinger-Keldysh contour. And the goal in holography is that I want to find a solution of Einstein's equations in asymptotically ADS spacetimes whose boundary is precisely the Schwinger-Keldysh contour, whose boundary in time, as I go to the boundary of ADS, mimics this contour. The strategy is to split the contour into pieces, is to chop off the contour into 3 segments. So I have my Euclidean segment, and I have 2 Lorentzian segments. So an observation in holography just from the Euclidean section is that at high enough temperatures, the geometry who is a solution of Einstein's equations, and it has a non-contractible cycle that is the thermal circle as its boundary, is what is known as the Euclidean cigar, with just a black hole, but it's not really a black hole because it's in Euclidean geometry, right? So here I present it to you. This is the Euclidean cigar, and here is the temperature is related to the horizon in this well-known formula. Similarly, if I now consider the Lorentzian segments, I want to smoothly continue or smoothly attach geometries to these Euclidean segments. So the usual way is I chop off my Euclidean cigar and I attach at a point of time reflection symmetry 2 copies of a normal black hole, right? So this is a black hole for the Euclidean segment, and the corresponding analytic continuation is just the black hole in the two Lorentzian segments. So this segment here is dual, is the cigar, and these two segments, their duals are two Schwarzschilds. I probably misspelled Schwarzschild. Okay. In the Lorentzian segment, it's convenient to introduce ingoing coordinates, just because I don't want to deal with artificial singularities at the horizon. I need to worry about analytic continuations across the horizon. But now, in the Schwinger-Keldysh contour, I have this complexification of the time coordinate, right? I have this segment over here, which is roughly t plus I epsilon, and I have this segment over here, which is t minus I epsilon. And now, in ingoing coordinates, the strategy is to keep the ingoing coordinate real. That is a prescription. So I will keep the ingoing time real, but that means I need to complexify the radial coordinate to cancel the complexification of the Schwarzschild time. Okay? And then, in summary, I have these two copies of the Schwarzschild black hole. This is just the Penrose diagram of the Schwarzschild black hole. I only consider the positive time directions because I want to consider this kind of contour that I set to start at t equals to 0, right? So I don't need the path segment of the black hole. And the interior doesn't exist. In this geometry, I'm only considering the exterior of the black hole. Real-time thermal correlators don't really know about the interior of the black hole. They do in certain analytic continuations, but the actual correlators don't know about the interior. And the idea is, okay, now I need to paste them together, and I do this. Take this point and extend it to infinity. That's free because I have unitarity. As long as I don't insert any operators, nothing forbids me to extend the point at infinity. And in ingoing time, the corresponding case is to consider the horizon all the way to infinity. And the prescription is join them together across their common horizon. So I have these two black holes, and I join them together across their common horizon. This can be done trivially. It satisfies the Israel matching conditions trivially. They're both vacuum solutions of Heisenberg's equation. They're actually pretty much the same solution anyways, right? And I'm not depicting it here because I am bad at drawing, but in these red lines, here you are connecting the Euclidean geometry that prepares the thermal state. As I said, it's useful to complexify the time coordinate and consider this kind of Henkel contour. So now in ingoing coordinates, I only have V and R. V, as I said, we keep it real. And all the information about the two different branches of the Schwinger-Keldysh contour just gets translated into conditions for the radial coordinate, right? So I have in principle, I have two sets of radial coordinates for this black hole and for this black hole, but I can just paste them together into a complexified contour that follows this kind of curve. So this is your right Schwinger-Keldysh contour, and this is your left Schwinger-Keldysh contour as you take t goes to infinity, right? To keep track of all of this, it's useful to introduce a mock tortoise coordinate. This coordinate is just engineered to capture the analytic structure of the solution. So I want just to keep track who is in the right branch and who is in the left branch. This coordinate tells you, or the coordinate is just pretty much R in any of the given branches, but it has a jump. This is just a hypergeometric function. It has a jump as you go from one branch to the other one. The coefficients in front and the integration constant is just chosen so the jump is exactly 1. This is just I could have made some other numbers, but the important thing is that the fact that you have two different solutions and they are connected across the horizon gets captured by this modified radial coordinate. So nicer picture. There is the final geometry that you end up. So this is a nicer version of this, right? So the thing that you end up is kind of what you want. You wanted a solution of Einstein's equations in the bulk which is this thing, whose boundary is the Schwinger-Keldysh contour, right? And a bit you don't need too much imagination to see that this is precisely the Schwinger-Keldysh contour for a thermal state. So this is the Euclidean part of the Schwinger-Keldysh contour. The two endpoints are identified in the usual thermal way, and these are the time right and time left. And this is the horizon of the black hole, right? And now you have your geometry, and if you want to compute things on it, you can just study the dynamics of fields on this geometry, and you can compute all kinds of things. You can compute two-point functions, you can compute higher order correlators via corresponding Witten diagrams. All this can be done. Many of these calculations I have done together with my collaborators Mukun and Loga, where we studied precisely these kinds of geometries uh, for higher order thermal correlators. This is just for the Schwinger-Keldysh contour. Okay? And this has proven to be very useful if one wants to study holographic fluids and one wants to construct real-time effective actions for fluids. One can use this geometry and study things like metric perturbations or graviton dynamics on top of this geometry. And from there, one can construct effective actions for fluids. So that's the Schwinger-Keldysh contour. I should ask here if there is any questions. People usually get lost with too many black holes. Good. Because now I'm just going to go wild. If there is no questions, I'm just going to copy paste black holes galore. Okay, so now, once again, we want to repeat the exercise and compute a ball solution of Einstein's equations, whose boundary is now not the Schwinger-Keldysh contour, but this more complicated geometry, which I call the gravitational Schwinger-Keldysh form, because it has four branches. So same story, consider four black holes. In this time, so you have, these ones are just like the ones before, they correspond to this branch and this branch. So I really only need the domain of outer communication, the positive time region. But for the other branches, I need the full thing. And once again, abusing unitarity, I extend the point where the contour turns around to infinite future and infinite past. I can just do that because I can just trivially insert resolution of the identity in form of unitary operators. So the intermediate situations are actually the full outer side of a black hole. And here I color coded in the way one needs to paste them. The way these guys are pasted follows the way the time contour is pasted. And so you have your first branch, which has its corresponding black hole, that again it gets pasted to one of these long ones that cover from minus infinity to infinity in time. So it gets pasted across their corresponding horizons. And then at a point in the past, this gets pasted to the next one. So it gets pasted in the past horizon, it gets pasted to the next, and etc. So this is just for four, but you can repeat this for as many as you want, right? You can just keep copy pasting black holes. The important part is that the first and the last one, they then connect. I didn't draw it again because I'm bad at drawing, but they connect to the Euclidean geometry that prepares the state that you want to study. In this paper, we really just focused on the thermal state, but this construction, you could do it for other states as well. For instance, you could do it for the vacuum, and all of these will just be copies of the Poincare patch instead of black holes, and you will need to include the Euclidean cigars. Also, we never consider putting sources. We will always put in the real parts of the contour. One could, in principle, put sources in the Euclidean segment and prepare some kind of excited state from the thermal state. So this construction, in principle, holds for all of those situations. But I will just consider the simple thermal state. So here is how it more or less looks once you copy paste all the black holes. So you have your four copies of the black hole pasted together in a particular way. Now, a new ingredient and something that is somewhat annoying is that in the case of the Schwinger-Keldysh contour, we were able to consider this single complexified radial coordinate that takes care of everything, right? It takes care of the pasting in terms of this Henkel contour. Now we cannot do that, right? Because we have 4 copies of the black hole. And not only that, but we're also pasting in the path horizon. So many of these black holes get pasted in their path horizon. So you need to change to outgoing coordinates, which are the ones that are smooth at the path horizon. So there is no way to introduce a single complexified coordinate that covers the entirety of the geometry. That's a bit frustrating. I would really have liked to have that. Instead, one needs to work with the geometry patch-wise. You have time and radial coordinates for each copy, and then they need to paste together in the way I, I told you, just across their horizons. Okay, so that was perhaps too kindergarten. Just take your scissors and copy paste your Penrose diagrams. But let's put a bit more meat in the bones and actually compute things. So the way I understand geometry, the only way I understand geometry in any sense, is I need to put stuff on the geometry. I need to throw some fields or some objects on the geometry and see how they behave, right? And that will tell me how the geometry operates. Here I will consider just a minimally coupled massive scalar, so like the battle horse of kindergarten holography. I will first study just the free field, but soon I will also consider interactions because I want to actually compute Witten diagrams. 2-point functions using these generalized Schwinger-Keldysh contours is overkill because 2-point functions, you can just capture all of them with the normal Schwinger-Keldysh. You really need to go to higher order correlators if you want to use these geometries. So here I wrote the equation of motion of the free field in the ingoing coordinates. You can also consider outgoing coordinates. You just need to reverse this sign here. Boop. That's the same equation if you use outgoing coordinates. And now we use normal holography. We say, okay, how does this field behave in the asymptotic boundary? I just solve this equation in the limit r goes to infinity. Since it's a second order differential equation, I will find that there are 2 Frobenius expansions across near the asymptotic boundary. In the holographic dictionary, I will just read one of them to be the non-normalizable mode associated to the source of this field, the J, right here. And the other one is the normalizable mode associated to the 1-point function in the presence of a source. If I was just computing 2-point functions, the general easy rule to do that is you take ratios of these guys. But more generally, I will have to actually solve the equations. I also need to know what the behavior of the field is near the horizon. So here is the solution. This one is boring because it's fully analytic at the horizon. It's just a Taylor series. This other one is the interesting one because it has this prefactor, which precisely is non-analytic. As I complexify R and I move it across the horizon, this will produce different phases. And notice it's proportional to the temperature, so this precisely captures the fact that the black hole is the correct dual for a thermal state. I need to start accelerating, so I can define ingoing and outgoing propagators. I actually only need to do it once because I can use time reversal to get the other one, so it's easier. So if I am doing a normal Schwinger-Keldysh, I just have 2 fields, one living on each branch. The ingoing propagator is analytic, as I mentioned, across the horizon, so the coefficients have to match. These 2 coefficients have to be the same because the field has to behave the same in one black hole or the other. It has to be smooth as I move from one to the other one. This one, the outgoing propagator, is not smooth. It has this phase. But I know in the case of the gravitational Schwinger-Keldysh 2, I have this Henkel contour, which tells me how to analytically continue the radius. So I just produce a phase, right? So this has to change to this from one side to the other one. And then you can impose the Dirichlet boundary conditions to read off the sources, and this is your solution in a gravitational Schwinger-Keldysh 2. The story for gravitational Schwinger-Keldysh 4 or n is the same. Just take many, many copies of your solution. The equations of motion are the same in any branch, so you can just take many, many copies of them. And the magic or the trick comes in matching conditions across the different horizons. Now you will have n copies of a black hole, and you need to match them across them. Now, the first ones are the ingoing solution is analytic in the future horizon. So in principle, I will match these coefficients. But I need to be careful because I also need to do matchings in the past horizon. And there the story is reversed. The ingoing solution is not analytic in the past horizon. The outgoing solution is analytic in the future the outgoing solution is analytic in the past horizon. So the matching gets a bit more complicated. One is to keep switching between ingoing and outgoing coordinates over and over again, but it's not too complicated. One can eventually obtain a system of equations that implement the matching in this geometry. I literally just imagine I have a field here, and I push it to the horizon. It comes up somewhere over here. The coefficient in the ingoing term doesn't change, and the coefficient in the outgoing term gains a phase. In principle, that phase is arbitrary, but I then fix the phase by matching in the Euclidean cigar. The Euclidean cigar prepares the state in the thermal state of a particular temperature that I want, and that fixes the phase to be the correct phase for the given temperature. So here is the solution. It's easy, it's convenient to write things as matrices because now I have n copies of the solution, and so things naturally arrange themselves into matrices. So I define a bulk-to-boundary propagator that relates the sources in the boundary to the field in the bulk, and this is it. This looks intimidating, at least to me at the first time, but the structure is very, very simple. There is really only three things you can have. You can only have fully normalizable functions, g in and g out, they just become the same in the boundary, and so this object just cancels. Or you can have two types of non-normalizable solutions, distinguished by this phase. And the structure of this just follows from KMS. If I impose that the corresponding correlators obey KMS, this structure just follows. Okay? So as I said, if I want, I'll just make the comment that one can trivially evaluate the two-point function, just evaluate the Gaussian part of the free action, and one gets this answer for ERSK 4. This is boring because you could have guessed this from just with contractions, because for two-point functions, having more and more copies of the black hole doesn't really buy you anything because you're just doing two-point functions. You're only ever connecting two of the branches anyway, so that's a bit boring. You could have guessed this from unitarity and KMS. To make things a bit more interesting, you need to consider Witten diagrams. So you want to actually consider something like cubic interactions and consider diagrams. Here you will input the solution we just constructed and evaluate the corresponding diagrams. Right? So technology of how to evaluate the diagrams, you can use this matrix technology to just write it like this. So this is, if I want to compute a three-point function, where all the operators are inserted in the first forward branch, this is what I will compute. These are the sources in the forward branch. This is just algebra, there is nothing too interesting there. The important thing is that if you remember, I have the difference relation. If I want to compute a three-point function of the difference operator, that should be zero, right? Because we have these conditions of unitarity, and one can check brute force from the solution that this is indeed zero. I'm not requiring this, one can just compute this and see that this works. Similarly, the KMS correlators or any of the many different difference correlators, you can check that the corresponding Witten diagram vanishes. So that's good. The guy we wanted to compute, the guy who is interesting, is the out-of-time order correlator, right? This is the object that I began motivating as to why do I need this generalized gravitational Schwinger-Keldysh contour. So this is the general structure of the out-of-time order correlator using the right-left basis. But now we find something not too nice, and is that if you compute this object using just contact diagrams, you will get exactly zero. It's a bit counterintuitive at first, at least, but then if you think about it, it kind of makes sense. This object should know about the fact that you are now really in a fourfold geometry, right? You're not just in disconnected copies of the twofold. This object should really be not capturable by normal Schwinger-Keldysh. Contact diagrams only interact pointwise per geometry. They don't really have any information about the connection between the different branches. In principle, for a contact diagram, at any moment when you are doing the contact interactions, the thing just looks like two copies of gravitational Schwinger-Keldysh. So it kind of makes sense that contact diagrams lead to trivial out-of-time order correlators. So this is this heuristic argument. So if you want to obtain non-zero answers, one needs to consider exchange diagrams, right? In which case one needs to work a bit harder and compute the bulk-to-bulk propagators. I will not bore you with the technical details. One can just compute bulk-to-bulk propagators. I'll give you the final answer. The final answer is ugly. This is more or less the bulk-to-bulk propagator. Clear with this. So step functions, they just come from the usual radial ordering of the bulk-to-bulk propagator. The important thing is the structure of this matrix. You can just guess it from unitarity and KMS. The bulk-to-bulk propagator is constructed so that the corresponding correlators satisfy unitarity and KMS condition, which is what fixes all these little phases and signs all over the place. And then one can compute the 4-point exchange diagram. It's a bit of work, but it's not zero. The important thing is that the exchange diagrams, according to this intuition I have, that out-of-time order correlators should know about the structure of the fourfold geometry. Indeed, the correlator is not zero, and the reason for that is actually simple, and it's the fact that when you do these calculations, you actually need to consider all the different channels, the usual S channel, T channel, U channel. Furthermore, there is a complication. You may think about this as Feynman diagrams, but Feynman diagrams are symmetric. You have translational symmetry in all the directions. The bulk-to-bulk propagator is not symmetric in the R directions. ADS is not symmetric in translations around the radial direction. So if you have this kind of diagram and you try to swap the ends, in normal Feynman diagram, you just get a symmetry factor. In this case, you get actually a different answer. And this is what, in terms of math, what makes this correlator not to vanish. In the case of contact diagram, this is exactly absent because you don't have any exchange diagram, and that's why contact diagrams do not contribute to the out-of-time order correlator. Furthermore, it's not only zero, it's very, very simple. And this was a bit of a surprise. If you do all the calculation, in principle, this is a mess. This is horrible. There is because you need to consider all the channels. There is all kinds of contributions. But when the dust is settled, the correlator just becomes this very nice factorized form. So really what you are discovering is a factorization channel where you can just compute this 3-point function, this 3-point function, that's what these W's are, and they are just connected in a very nice way. This was unexpected because in principle in the bulk-to-bulk propagator, you need to worry about radial ordering, but all that just disappears for the out-of-time order correlator, only for them. Any other complicated 4-point function you may want to compute, in general you end up with some complicated relation, but the out-of-time order correlator has this nice factorization channel. And one can repeat the story for, I have like 5 minutes left, but one can repeat the story for higher order correlators. I can just, the geometric construction is trivial. I just copy paste more black holes. But the important thing is to impose the correct unitarity and KMS condition to compute your ball-to-ball propagator. And if you want to look for non-zero contributions for a higher order OTOC, this is the kind of diagrams that contribute to that. Once again, the reason why these diagrams do contribute is that it has the correct symmetry on the permutations of the labels. So we have a conjecture that we have not quite proven, which is that in the same way that for the 4-point out of the model correlator, contact diagrams do not contribute, again, by the intuition that you need enough exchange legs to actually explore the full ball geometry. If you consider a higher order out of the model correlator, once again, you need a higher order of degree on your exchange diagrams to have non-zero. The reason why this is a conjecture and not a proven thing is that just combinatories, we run out of energy, because here is an example of a diagram that contributed this ladder diagram. But as you increase the number of n, of the order of the correlator, not all diagrams are ladder diagrams. So you will need to start worrying about more complicated topologies for your tree diagram. And also, we make no claims about loops. So just to conclude, this was a very direct generalization of these gravitational Schwinger-Keldysh contours of Glorioso, Liu, and, and Crossley. There is another prescription in the literature, which is due to Eskenderis and Van Ries, in which they consider these kinds of constructions. They consider two copies of the black hole as well, and instead of complexifying the radial coordinate and keeping the ingoing coordinate real, they just work in Schwarzschild coordinates all the time. In that case, we need to be a bit mindful of the analytic continuation across the horizons. But here we did that analysis. Something cute about this is that there was this simplifying property I used to construct the geometry, which is that I use unitarity to arbitrarily extend the branches to the future and to the past. You don't really need to do that. In this construction, you can just consider finite size Schwinger-Keldysh contours. So this is for the twofold. This is for the GRSK2. But what we did in our paper is one can extend this for many black holes. Here's just 4, right? And just repeat the analysis. And I didn't put it because it gets messy, but one gets exactly the same ball-to-boundary and ball-to-ball propagators and the same correlators and in the complexify radial coordinate prescription. Okay, so that was mostly what I wanted to talk about. I just want to mention a few conclusions and future directions. So we constructed this generalized gravitational Schwinger-Keldysh geometry. All the information about tree-level Witten diagrams is captured by ball-to-boundary propagators and ball-to-ball propagators, whose structure is dictated directly from just unitarity and KMS condition. We have this result that contact diagrams do not contribute to the out-of-the-model correlator. You need to go to exchange diagram. That was the important result, but corollary of that, fun surprise we encounter is that not only is the OTOC interesting for all the reasons we know about chaos, from the point of view of just Witten diagrams, it seems to be a preferred channel that obeys this nice factorization. As I mentioned, for future work, something that was a bit frustrating is that one needs to work with just piecewise coordinates. I need just to have different coordinate system for my black holes. In the case of the Schwinger-Keldysh contour, I could introduce a single radial coordinate that has a two-sheeted Riemann surface structure, and that just allows me to have a single complexified coordinate for the full two-sided geometry. We don't have that for the n-sheeted geometry, but it's something that one can think about. Just think about these GRSK geometries as some more complicated Riemann surface, and see if one can made up the corresponding mock tortoise coordinate similarly to this theta that I introduced for ERSK2, so that you can do everything with a single coordinate system, and then you don't need to deal with these big matrices that I showed earlier. Another thing is that one needs to carefully, as one increases the order, one needs to carefully classify all the constraints of unitarity and KMS. It starts to get messy when you go past 6. And so one needs to carefully do this for higher order. Uh, Something that perhaps people will be interested on is if there is any relation between these results and the thermal bootstrap. If one consider CFTs in some large N expansion, is there uh, an image of these particular factorization channels and results from Witten diagrams that translates into conditions for the factorization channels in CFT? Another thing that was a big motivation for me is if one can, in the same way, one can use the Schwinger-Keldysh, gravitational Schwinger-Keldysh contour to construct effective actions for fluids. One could now use these generalized gravitational Schwinger-Keldysh contours to construct effective actions for chaotic dynamics. Some people have started doing that, motivated mostly by the story of Paul Keeping. One could try to use these uh, gravitational Keldysh contours to construct more directly the corresponding effective actions. And finally, even though all I care about here is standard holography, uh, the way I like to think about these geometries is that how can I make sense of the Lorentzian gravitational path integral? Usual holography allows me to very concretely make sense of the gravitational path integral, and one can imagine how can I generalize this from non-ADS settings. For instance, if I want to consider flat holography, or if I want to consider cosmological correlators uh, beyond the traditional Schwinger-Keldysh contour. So that's it, and now I'll take any questions people may have. Thanks.